We'll begin, looking at dynamic routing now. Prior, we've been treating static routing, right? And when we're saying static, we've seen just like driving cars, you've seen manual and automatic, right? Static literally is you manually typing out the IP addresses, the IP routing. Like imagine when we did that 4 network system, how you had to do IP routing for how many networks, because each router was connected to 3 networks, so 3 times 4, that's about 12 networks. Now you have to IP route for at least, each router needed to be IP routed for like 4 networks. So lots of manual labor, and that's just for something of just 4 routers or 4 or 12 networks. Now imagine if you want to do for a city or an entire, let's say, a company with, let's say, multiple story buildings and multiple networks. This is really going to be a super Herculean task to want to manually, to configure that network with static mode, right? So that's why we have dynamic, and we're going to be, having a lot of exciting time, especially during the course of this program. So can we define the definition of dynamic routing on our screen?
Dynamic routing uses the routing protocol that dynamically discovers network destinations and how to get there. Dynamic routing allows routing to change if a router on the route goes down, or if a router on the route goes.
Or if a network is added, right? So like we're saying, like you say, dynamic routing uses a routing protocol to dynamically, it discovers network and their destinations, and it knows how to get to them, how to ensure packets goes round amongst all of them. And whether dynamic routing allows routing tables in routers to change if a router on the route goes down, right? So a lot of times, one thing about, even just like when we're talking about DHCP, you can connect to a router at this moment, and if, say, the IP address it gave to you was, let's say, .20, if that router goes off, or let's say you leave and you come back, you will not receive that .20 again. You might receive .12 or .40 something within its range, if it can assign IP address from .1 to .100. So most likely the router itself is going to have the .1. Then every other hosts are going to share network ranges down to, .100. So it's always going to automatically assign all of these things. So whether a new network is added, that one will receive an IP address. If one goes down and comes back up, it's going to receive an IP address, right? So that's really what we're talking about. So now we have like this table, kind of like that I'll use for like the differences, right? Differences between static routing and dynamic routing, the versus, right? And for static routing, we can see they are manually configured routing entry, right? And we know that dynamic uses routing protocols that dynamically discovers network destinations and how to get to them. Static routing must be manually updated if topology changes. So if a computer or a host leaves and is being re-added, you have to go, once you're reconnecting, you have to give your manually assign an IP address to share that network. It is suitable for small networks, and one of the advantages, it has less CPU usage, right? But that might not really be important in this current generation, because of course, who uses those old PCs that so may be fine to use to or from a stub network and is very easy to implement. For dynamic, automatically updated if topology changes like we said, suitable for large networks. Yes, so that's what you need if you want to interconnect an entire city or village or even a big company, right? And rapid convergence, so it always requires faster devices with higher CPUs. Now let's look at how dynamic protocols works, right? So it sends and receives routing messages. So it shares messages with other routers. It exchanges router information with each other as router topology changes to others. Okay, so I'm going to take like a pen or a marker rather to kind of like depict what we're talking about here. Let's just kind of like have that description of say what exactly it is we're talking about. Let's say we have like three routers. Let me just use the let's say we have three routers. Okay. And these routers have their own connection to a PC. Let's say they are connected to a PC. Okay. Let me say this one has two. This is another switch. This is a separate PC. The same thing for this one. The same thing for this one. So, in a dynamic routing system, right? Once they are on that mode, do you know what they will always be doing? They'll just be sending packets to themselves. Like you may not be seeing it. Hey guys, I am Samuel, and I have this network connected to me. This one will be like, hey, nice to meet you, Samuel. I'm Prosper, and these are the two networks connected to me. So they are doing these things to each other like this. They are busy sending packets, right? So each of them is already aware. So they are like aware of the topology of the network. When I say topology of the network, right? Okay, this router has two networks connected to it. Okay, it's like four because 1, 2, 3, 4, right? So it has that. So all of them are aware. That's what we're saying. They are sending and receiving routing messages to themselves. Because even if a PC goes off, others will know that, okay, a PC have left this network. They exchange router information with each other. They advertise topology changes to others, right? So I don't know if this better explains what we're talking about. Does it? Okay. So now we'll be looking at, the dynamic routing protocol. And I was trying to tell you, the interview I was in, this was literally where they focus all their questions on. It was literally on the dynamic. He asked me, I should talk about VLAN and trunking. I said, okay, great. We did IP routing. He said about the types of IP routing, right? Static, dynamic. So he give examples, 2 of each. I gave him. Now come and ask me. This was the one for dynamic I mentioned, EIGRP. He said, is EIGRP a distance vector or a link state? I was like, I cannot remember. It's been a while. So it really upset me. Up till now, it's still paining me. Right? So dynamic routing protocol classes, right? So this is like a tabular form for something that would really, really be important for you, right? We have the interior gateway and we have the exterior gateway protocol. Interior gateway is like what the dynamic routing actually uses. So that's like IGP. EGP is something a little bit different, right? You can just take this for example, say we have like a set of network here. This is like two routers connected to each other, right? This is like IGP, right? And here too, you have another two router connected to each other. Let's say there's like a cloud here. So these two guys, these are like two different these are like two different dynamic routing systems, right? So if there's ever a need, say, okay, there's ever a need where you want these two different IGPs to intercommunicate, that might be where the EGP would come in. So it is way, way higher than the IGP, the external gateway protocol. Is the one that helps, it comes in that, hey, this internal gateway protocols, two different internal gateway protocols want to communicate with each other. So they cannot go external. Like at least this box that I did here should help. So it is the one that helps make that possible. So it's something that can handle something much more than that, right? Now, but there are two main types of, two main classes of routing protocol. We have the distance vector routing protocol, and we have the link state routing protocol, right? We have the, what are the two classes of routing protocol, guys?
Distance vector routing protocol,
Link state routing protocol. And examples of the distance vector routing protocol are the RIP and the EIGRP, right? They are the RIP and the EIGRP. And for the link state routing protocol, there are OSPF and ISIS, and we'll really be looking at that shortly. What this simply means is RIP v1 and IGRP. Those are the first versions of IGRP, is first version before it became extended EIGRP. And we have RIP version 1 and currently we're on version 2. For IPv6, it is RIPNG, EIGRP for IPv6. Then OSPF version 3, ISIS, that's for link state. Now, we are going like into the definition of what exactly distance vector protocol is. So, distance vector protocol routes according to the hop count, right? Distance vector routes according to the hop count. By now, we know what hop is, Abi. Spoken about hop. That is, every router knows as much as the other tells it, right? There is no network map on the router, e.g. RIP, EIGRP. So like this instance that we are talking about, you see, they are always exchanging data, right? So if this router does not give that feedback to this guy that I have a network behind me, it will not be aware, right? So the next hop, like we said, if you ever want to send a packet to this guy, say a PC here, or let's say a PC here, right? You want to send a packet to a PC here. The next hop to that is this interface here connected to this router, from this router here that wants to send that packet. Now, we already said that. So distance vector, like you're seeing that, right? Distance vector is comparing the distance. It looks, what's the fastest way for me to send or receive this packet, right? So it goes to the next hop, which of course is going to be the interface at this point, right? And through here, it sends that packet, right? So that's really what distance vector is all about. And that's how RIP and EIGRP works. Some of these things, once we actually begin doing them, the understanding will get way better, right? And we have link state protocols. And how that works is that routers can extract the topology map of the entire network, right? So a router, or if you want to use multiple routers in this case, they will know the entire topology map of the entire network. That's all the devices that are connected, all the PCs available, all the hosts, all the PCs, everything on that network. They will extract all that information, right? They can extract the topology map of the entire network. That is, they have the knowledge of all the ways between 2 points. So between 2 points, all the ways between 2 points. Thus, they collect all subnets in a tree and make the best decision about which way to go with the shortest path first protocol. So that's what OSPF means. Open shortest path first. So since it has all the network, like this one, for instance, the distance vector is only dependent on the information it's receiving from the next hop. What network do you have here? So it's just looking only focused on that distance. But for the link state, you have all the subnets of the entire network set like in a tree, configured into the routers. Now, whenever you want to send any packets, it looks at it. It looks at, okay, that's why in OSPF now, you could be seeing something like this. Let's say we have a router here. This router here is close to this router, and then there's another router that is far here. I think I should always not forget to do our configuration to make it appear like. So you see, for this now, in OSPF, right? Let me do something. Let's say the network is here. So the distance between here and here is very far. Let's say this router here wants to send packets to this one. Or rather, let's say this router here wants to send packets to this one. Right? Now, because of OSPF will look that, hey, the distance between here, like the router is literally connected to it too. It has access to it, but say it will look and know that the distance between here and here, let's say is 30 meters, right? But the distance, say this one is R1, R2, R3. And then the distance between R1 to R2 is 10 meters. And here too is 10 meters. OSPF is going to, or link states, is going to use here to send that packets. It's going to use through the router too to send that packet, because that is the shortest path for him to deliver that packet. But for distance vector, since that's literally the next hop, it will just send the packet to it directly, right? It's working with the information of the next hop it has. but OSPF has all the data of everybody, so it knows which way to follow to deliver packets the fastest, right? And now there could also be other arguments of if this place here now is fast Ethernet connection, the fast Ethernet, and this place here now, despite is longer, but it's a gigabit. Now, with the OSPF now send the packets through this shorter path or here. So we'll look at which one is going to deliver the fastest and the quickest, and that's the means through which that packet will be delivered, right? We also have path vector, which is, routing information is used to determine the best routes. In path vector and similar to distance vector router, they do not have a network mapping. So it only focuses on the best routes for that packet to be delivered. Now let's look at, difference between distance vector protocols and link state protocols. Right? So distance vector require that a router inform its neighbors of topology changes periodically. Right? So if a network leaves or a network is added, let's say in this connection that we did here now, if one PC here leaves in an EIGRP or RIP, this network here, this router is expected to inform its next hop, meaning this guy is here and this guy is here, that hey, this PC just left or this PC just got added, right? But for link state, you don't need to do that because it has the complete map of network topology. So it already has a complete map. So if anything leaves, it will know. If anything is added, it will know. Then it chooses the best path relying on topology table. So based on the topology table information it has, it chooses the best path to deliver its packets and information, right? So it doesn't depend on any neighbor, no neighbor dependency. Like you've seen from EIGRP, it's dependent on the neighbor. Neighbor being the next hop is very much dependent on it. So without receiving, if it's not getting any information, like we said, from the next hop, if this router is not getting information periodically, it will not know what's going on. But for here, once all the information is configured, it does not depend on anybody. It already has the data of everything. So it can always take decision on its own periodically or however it wants. And of course, we've seen that examples of each. For distance vector is the RIP version 1 and 2, and the EIGRP. For link state is OSPF and ISIS. So I think this is a routing protocol comparison chart, right? Another really very exciting thing that would be nice we look at and explore. Comparison chart, like you can see, we have characteristics and the type is listed under the characteristics section. All of them, like the network by its characteristics. So whether is it distant vector, link state, classless, VLSM, size of network, metric, convergence time. Okay, the characteristics. Okay, that's that. So for distance vector, we've seen that who are those under the distance vector characteristics? The RIP V1, V2, and EIGRP. For link state, we've spoken before that ISIS and OSPF are examples of link state. Then classless, the version 2 RIP down to the BGP, they are classless. Okay, we'll talk about what classless is shortly. Remember, BGP is like the opposite of the IGP. It's a type of the extended gateway protocol. You can see it here. So path vector, like we were talking about, is from the EGP, is for the EGP. That's what the EGP uses. So now, size of network, RIP v1 and 2 are small. You use that for like small network, but you can use EIGRP to OSPF for large network and BGP for very large network. And remember, this is like the BGP instance that we said, when there are already two different large networks, you still want to give them that external communication, right? Then of course you can look out for utilizing the BGP, right? And what are the metrics for that communication? You see, RIP v1, v2 is heavily dependent on the hops, right? On the next hop. EIGRP is dependent on the composite metric. ISIS dependent on the metric. OSPF cost. So what is the cheapest and most efficient way for me to deliver this packet? BGP path attributes. So convergence time, RIP is slow, EIGRP is very fast, ISIS and OSPF are fast, but BGP is very slow, right? Now, we'll now be looking at RIP. We'll be looking at all of these guys literally like, one after the other. We're looking at all of these guys like one after the other. So RIP and RIP.